Yeah, so as Jeremy said, I've been looking at superoptimization. This was funded as part of an Innovate UK feasibility study into commercialization of superoptimization. And so I'm going to talk a bit about if we can commercialize superoptimization. But first I'm going to talk about what it is and new developments of superoptimization. So firstly, what is superoptimization? Compilers, you can turn on your -O flags, you can turn on O1, O2, and they will optimize. They'll make your program better, faster, but not optimal, not the best possible it could be. They just make it slightly better. So this is why we have superoptimization. This is producing completely perfect code, and we get perfect code by trying everything. So as you can imagine, this is quite expensive. This is a term, the superoptimization is a term first developed by Henry Maslin, who went through every possible instruction sequence to try and find the shortest possible he could. So, every possible instruction sequence. There's quite a lot of them. So, for example, take x86. We just take a small subset of x86, we've got about 400 instructions. So, if we want to explore, say, just up to 3 instructions, we've got 64 million different instruction sequences to consider, which is not too bad. We can probably search that quite quickly with some supercomputing. But say if we go a bit higher, say 10 instructions, it's suddenly quite infeasible. That's 10 with 26 zeros after it, and I haven't done the calculations, but it would take a very long time to check. So we've got lots of instruction sequences, and we want to pick the best one, and we want to pick the right one. So we have a length L. The number of instruction sequences we have to consider is the number of instructions in the instruction set, the power of the sequence length. So if we have a bigger instruction set, like x86, we have to consider more instruction sequences. If we have a longer sequence, we have to consider more instruction sequences. So that's a very brief overview of what superoptimization is. It will become more clear as I talk about it a bit more. So I'm going to talk about superoptimization. What is superoptimization? What are the main components of a superoptimizer? And then I'm going to talk about some of the new academic developments in the last 10 years. So people have been gradually dabbling in and out of superoptimization, trying to improve it, trying to make it feasible for everyday use. And then I'll talk about the GNU Superoptimizer, which is a fairly old piece of software, but still probably one of the best superoptimizers we have. So, what is superoptimization? So, as I said, it came from Henry Maslin's paper many years ago now, where he took a very small Motorola 68000 and wrote some code, ran on there, and just went through every possible instruction sequence, ran a few tests on it until it gave the right answer. And if you test it a number of times, you can be slightly sure that it does the right thing. So I'm going to give you an example of some of the things that he found. So here we have a very simple function. It's just taking a number. If it's positive, it will return 1. If it's negative, it will return -1. If it's 0, it will return 0. And you put through a compiler, you get these instructions here. You can see at the top it's doing a comparison. And it's branching to various different bits of code depending on what the value is. So here we have 3 jumps, of which 1 or 2 will have to be executed, and a total of 8 instructions. So we could probably do a bit better. And Henry Maslin put this into his superoptimizer and came up with the following sequence. These 4 instructions here, which do the same thing as this piece of code here, but not in a way that's obvious at all. So I'm going to walk you through this set of these 4 instructions so you can see how weird and wonderful the sequences superoptimization comes up with. So we've got our 3 different test cases. We've got a negative number, we put it into D0. We've got a positive number, and we've got 0. So initially, this instruction doubles it. This has the side effect of putting a 1 into the X register, which is the Motorola's carry register. So we have 1 in there if it's positive, 0 in other cases. And then the next instruction does subtract, which is also part of subtract carry. So it subtracts D1 from D0, D1, which has the effect of zeroing out D1 if there's anything in there, and subtracting the carry over. So we then have -1 in D1 if it's positive, 0 in the other cases. The negx instruction has a side effect of, if the number is not 0, it will put a 1 into the x bit. And so we now have 1 in the x bit if it's positive or negative, 0 otherwise. Then the final instruction just does an add of D1, D1 to D1 and adds the x bit as well. So in this case we add 2 lots of D1, so we get -2, add the 1, we get back to -1. If we have 0 number registers, we stay with 0. If we have 1 in the x bit, we end up with 1. So you can see it's taken quite a while just to explain what these 4 instructions do. And Superoptimization has the potential to find weird and wonderful sequences like this. So stuff which exploits the carry bit, stuff which exploits weird instructions which you normally wouldn't think of using, and typically comes up with results that people...
Just to avoid confusion, you've actually got the very last box there, I think should have a 1, which means 0 minus 4, 1.
Yes, that's right. There should be a 1. Yeah.
Sorry, can I just ask?
Yeah, sure.
Is it optimizing for CPU cycles?
It can do. In this case, it's just trying to make it as small as possible.
So it's just instruction count?
Yeah. So the way Henry Massman did it was to look at all of the sequences of length 1, and then length 2, then length 3. When he found a sequence which passed all of its tests, it was going to be the shortest one, so he checked every other one. You can do the same for cycles, as we'll see. Yeah, so it uses the CPU in weird ways. And this instruction sequence here is about half the instructions that the compiler came up with, and at the time it was about 40% better than most people knew how to write it by hand. So pretty good. But still limited to short instruction sequences. So that's what we can find for Superoptimizer. What's normally in a Superoptimizer? So there's 4 basic steps to any search procedure. We have to enumerate all of the instruction sequences, all of the potential candidates that we're looking at. And because there's so many of these, we want to have some methods of reducing this number. So we'll prune them a bit. Then we want to test, is the instruction sequence producing the right output? We've got our input function, we've got a load of candidate instruction sequences. How do we work out for the same? And then we want to cost it. If is it the best? Is it not the best? And then if you put these 4 things together, you'll get a Superoptimizer. So I'm going to talk a bit about each of these in turn. So looking at all of the instruction set, most Superoptimizers currently restrict themselves to a very small subset of the instruction set. So looking at arithmetic instructions, looking at bitwise instructions. Memory operations have been done in newer Superoptimizers but are very tricky to handle. Branching and loops are very, very difficult, and so far nobody's really attempted to do that. The problem of actually working out whether 2 programs are identical is not decidable if you have loops in them. So there's advantages to having a large subset of instructions and a small subset. If you decide to use all of your arithmetic and bitwise instructions, for example, then you might be able to find a solution a lot quicker than if you just restricted yourself to a portion of that set. However, your result might not be optimal. So you have a large subset, there's going to be instructions which are perhaps unusual, which perhaps can be combined in nice ways with other instructions and give you an unexpectedly short sequence. And we can there's 2 ways we can typically select the instruction sequence. We can just enumerate all of them, or we can go through randomly. And newer studies have looked at machine learning and try and predict which area of the search space to go into next. So we've got our list of instruction sequences we should look at. Which ones do we want to quickly discard? So once you look at a list of instruction sequences, it becomes quite clear quite quickly that most of them aren't possibly valid. There's instruction sequences which put stuff into registers which aren't ever used. There's redundant computation. There's stuff which shouldn't be there. And so these are stuff which is definitely not optimal. There's other stuff which you might have explored before. So the add R1, R1 is functionally the same as add R0, R0. It's just registers different. And the same with some of the operations as well. For multiply, you can have R1 on one side and R0 on the other, but it's the same as having R0 first and then R1. So using these things, you can think about the instruction sequences, you can reduce them quite a lot. So I'll talk about that a bit more and how much faster that speeds things up. So that's pruning. On to the testing. This is usually the hardest part of the Superoptimizer and the slowest part. So we have this instruction sequence. How do we work out if it's the same as our target function? Most kind of take a testing approach. So you just either you simulate it or you actually run it directly on the hardware and check the output. You do that lots of times with different inputs and check that you're getting the right result. If it is, you can either accept it or you can do some sort of symbolic equivalence test. You can use SMT solvers to prove that two instruction sequences are identical, although that's very slow. So on to costing. Which sequence is the best? For code size, that's quite obvious. It's just the shortest one. It's easy to measure statically. It's easy. You don't have to run it or anything. With execution time, it's a bit more challenging. If you have a small embedded processor, it's usually quite easy because you know the exact cycle counts of each instruction. However, in superscalar processors, it's quite difficult. How do you know which sequence is best? It often depends on the context around it. It depends on various things like whether it's in cache or not. It's quite hard to work out how long your instruction sequence is going to take. And energy. Again, another challenging one. You could either run them all and measure them, although then it's a problem that you're measuring such a short sequence of instructions. Or you can use energy models, but then they might not capture some effects. So code size is generally the easiest one. The other two take a bit more thinking about. So that's the fundamentals of the Superoptimizer. What is in a Superoptimizer? Now I'm going to talk a bit about some new developments. So I'm going to talk a bit about new techniques in those four fundamental areas. I'm going to talk about new Superoptimizers which have been developed. So search space pruning. I mentioned that we have all of these candidates which we need to look through. To discard some quickly, we can put them all in what's called a canonical form. So that's basically registry naming. If you put all the registers in ascending order, and we call that canonical form, and we can discard the sequences which aren't in that canonical form quite quickly. And we can do some things like restricted parameters. So it turns out if you take 8 instructions in a row, most of the time, about 50% of the time, they'll use only 4 or less registers. So if you're reasonably confident you can get the optimal sequence with that, you can restrict it to 4 registers. And if your instructions take constants, you can restrict it to frequently used constants. If you don't restrict it, then having a 2 to 32 space to explore really slows down the search. And then there's stuff like removing meaningless constructs, so moving the same register into itself and adding 0. They don't add anything, they're just making the instruction sequence longer. So I'm going to discuss canonical form a bit more. So take a simple example of a move instruction. If we have 16 total registers, there's 16 times 15 equivalent versions. And we can rename each register so that it appears in sequence. So here we have R1, R0. All of these are equivalent. This leads to quite large reductions. So if you do it for an instruction sequence, as an example, and if you have a 3 operand instruction, you have only 5 unique forms, whereas if you didn't have this, you'd have 16 possible registers there, 16 there, and 16 at the end. So that's a lot more than 5. So, how much does this actually reduce the search space? By quite a lot, it turns out. So, 16 ops, if we assume 16 ops, 16 different operations, and 16 each using 16 registers. Here we have the normal search space, which doesn't even fit the screen. So that's many millions of different instruction sequences to look at. If we use this registry naming, if we put each one in canonical form and only explore one version, then it's a huge reduction. It's half the power of the search space. And then again, if we restrict ourselves to 4 registers, it's smaller again. It's about an order of magnitude smaller. So this massively increases the number of sequences you can look at and your chance of actually finding a result with the Superoptimizer. So this has turned out to be a key technique which is enabling Superoptimization. Okay, and if we take a reasonable test rate, we can do it in 16 days instead of 2.9 million years. Which is good. So, testing instructions. As I said, to symbolically test if they're equal, it's very, very slow. You can only do on the order of 50 tests per second instead of about 200. And it's also restricted. If you did fancy attempting loops, then you can't do it. Test cases are simple and easy. You can just choose a set of input, you can run it, simulate it, and check the output. And that can be a very quick statistical guarantee or not whether it's correct. If it fails the test, you can quickly discard it and go on to the next one. Or, as in the original paper, you can just run it all directly on the same machine, write it to a bit of RAM, jump to that location, execute it, jump back, see if the results are correct. So this is mostly saying, as I said before, it's quite difficult to cost if you want to do it with performance. One of the most recent studies has just used it based on the functional unit latency, and they summed it up for different instruction sequences. So if we had an add, it takes X cycles for an add, and then we have a multiply, it takes X cycles, Y cycles for a multiply, so total cost is X plus Y. However, that's not really taking into account any sort of uniform pipelining or parallelism inside the CPU. If you could do some sort of accurate pipeline modeling, then you could get a good, quick guarantee of how fast it could go. But we don't typically have models for the superscalar processes. Cool, so those are the few new developments in the actual fundamentals of superoptimization. Now I'm going to talk a bit about the actual superoptimizers themselves. So lots of people have tried to build a good superoptimizer, and we have a few different takes on how to do it. So I'm going to talk a bit about the GNU Superoptimizer, and we'll talk about this more later. There's a section of detail on it. And then I'm going to talk about Denali, which is a completely different approach at trying to use this symbolic solver to get instruction sequences without explicitly searching for them. I'm going to talk about a peephole Superoptimizer, which was mainly for using compilers, so it was generating peephole optimizations which would then be reused in a compiler to allow speed-ups without having to rerun the Superoptimizer. Then I'm going to talk about stochastic Superoptimization, which is using machine learning to jump around that search space and try and guess which area you should explore next to give a good result. And there's a couple of others which I won't cover, which is Toast, which is a similar idea to Denali, and there's a hacker system which is very similar to the GNU Superoptimizer. So, onto the GNU Superoptimizer. It first focused on the elimination of short basic blocks. So, if we had a statement like this, we were just checking 2 variables and then incrementing another one, your compiler would compile to something like this. And they were trying to find branch-free equivalent pieces of code so that if you had a very long pipeline, you wouldn't need to flush the pipeline and this would go faster. And it was pretty successful, and a lot of the peephole optimizations found still exist in GCC today. So it finds a rewrite. It finds that you could do this, you do subtract, and you can add the carry bit. And then that gives you the same result with 2 instructions instead of 3 and no jumps. So the GNU Superoptimizer did have a few problems. There was no verification of the solutions. So there was a large statistical test. You ran lots of tests through the sequence. You were pretty sure that was correct, but you weren't sure that there wasn't some corner case where it didn't quite work, which is kind of important when you have all of these weird and wonderful features of the CPU used. If you're using the carry bits in conjunction with various modes which aren't typically exercised, or things which you don't quite know what's going on at all times, then you should probably verify that the sequences are the same. However, that being said, they didn't find a wrong sequence. The way it achieved the speed was you wrote it all out in C, compiled it in, it optimized, and then it went through brute force and everything. And then all of these were added to one of these peephole patterns. So I'm going to talk about this a bit more later on how you can add your own functions to GNU Superoptimizer, how you import it into architectures you've got. So on to the next one, Denali. So they used a constraint solver to say, we've got all of these instructions and we can encode them as constraints. And we have our target function, we can encode that as a constraint too. And we say, can we make these two match? What sequence of instructions do we need to make this match? And they basically ask the solver, can we do it in less than k cycles? If it replies with yes, it gave you a result, and you then decrease k. And then to decrease k until you couldn't actually find a solution, and then the last one you got was the most optimal solution. So that's a good idea, but they never actually mentioned whether it was successful or not, so probably not. It was a nice idea. They used all of these transformation rules as well, so they used to automatically work out if it was better to do an x times 2 or shift x up by 1. So that was a nice idea to have all of the transformation rules. However, you've got to add the transformation rules there in the first place. And if there's anything non-obvious, such as some of the pieces of code that we've seen before, you won't necessarily find them with these type of rules. So that was a nice attempt. So a bit more successful next in 2006 was a peephole superoptimizer. So this took a slightly different approach in that we're going to iterate through every possible instruction sequence, and we're going to work out which ones are the same as a predetermined list of superoptimization targets. So we've got lots of superoptimization targets, and we're going to go through every possible instruction sequence and work out if any of them are the same. We can then store these for later use, so we'll have groups of pieces of code which are identical, and we can substitute in any of these. So the compiler could then use this database. It can look up and see if one of its instruction sequences is in this database, and if it is, it has access to other equivalent instruction sequences without having to run the superoptimizer again. So I'll talk you through a bit how this actually worked. So you started off with a load of training programs, and then you harvested different instruction sequences from them. So you went through the program and you looked at every instruction sequence of length 4, for example, and you put it through the canonicalization again, and a fingerprinter, which put it in a hash table. So then we've got a list of all of the possible target things, all of the small instruction sequences that we have in this hash table. We could then go through every possible instruction sequence, we'll enumerate them all, compute the fingerprint again, and see if the fingerprints match. And if these two fingerprints match, it's a statistical test, it might not be correct, so they did a Boolean equivalence test, which is using a solver to prove that they're the same. If it finds two instruction sequences which are the same, then it puts them in this database for later use. So that's how we construct our optimization database. And then we can use the optimization database. So we put the input program, the compiler peephole pass goes through very small sections of code, analyzes them, fingerprints them, and then looks up in the optimization database. If it finds that small piece of code in there, it can enumerate the possible replacements, and if there is a replacement, it can do a replacement. And by doing that, you can get pretty good results. It doesn't give you as good results as just doing a super optimization on various bits of your program, because it's by definition only looking at very small segments. However, they managed to get an equivalent level of optimization to GCC 03 without applying any other optimizations. So they'd take code from GCC 00, just put it through this pass, not apply any other optimizations, just using that optimization database, and they were able to get equivalent performance to GCC 03, which is pretty good considering if you could do that, it would take a lot of the effort out of writing a compiler. You could just put it on a supercomputer for a while, compute all of these possible peephole passes, peephole optimizations, and then you distribute the database along with the compiler, and it's significant effort produced. So that was a nice study. There was
James, can I just ask, did they actually try and see if you started with a tree, did it do better?
They didn't really, no. Which makes you think that if you were to start at 03, you probably might not get much better. So while it's good for accelerating compiler development, it might not be much better for actually improving the code. However, the next study did manage to do a lot better. So their main innovation in this was, instead of just going through every possible instruction sequence, we'll take a beginning instruction sequence and then we'll look at instruction sequences around it. So we'll perhaps change the first instruction from an add to a subtract and do various kinds of mutations like that, moving around localized parts of the search space. And by doing that, they had a cost function as well. They said, how close is the final result to the one we need? And then it could kind of make its way through the search space to the correct solution based on this metric. So by using that, they were able to explore really long sequences because they didn't need to actually consider every possible part of the instruction space, instruction set sequences. So you could view this as a very effective pruning method. So their headline result was they took a Montgomery multiplication kernel out of OpenFSL and managed to improve it by 40% over what GCC 03 managed to do. So they got an extra 40% out of this high-performance kernel, which expert programmers hadn't seen. It was pretty good. And the interesting thing about this was it was a completely different algorithm. Whereas their code, the code written and then compiled, performed the multiplication one way, the Superoptimizer found a different way to do it by parallelizing different bits, using different partial products of the multiplication and combining it in different ways. And it turned out to be a lot faster. So, like I said, they used metrics to try and push them towards the correct solution. So they used a number of bits different from the correct output, and whether the correct output was produced in a different register. And it's not that obvious why this would actually work. It relies on the target function you're putting in having lots of output, not reducing to a Boolean output, but filling up the bits in a very specific pattern. And that's how they managed to guide the code, guide the search towards the right sequence. It's a form of intelligent hill climbing. And they have this very nice diagram in their paper, which is showing the difference between optimization and synthesis. So they make the difference that you could first start with a random instruction sequence. So all of these, the blue is correct programs, functionally equivalent, but perhaps a different performance. And the two little bubbles are, the right happens in one particular form, there's a different algorithm which does the same computation on the left. And then they made the distinction between, you could start with unoptimized code and use this method, but it would only optimize in the same way that the compiler would. However, if you start off with a completely wrong instruction sequence, just start somewhere randomly in the space, you could then meander towards a correct solution, which may or may not be algorithmically different. And then it just so happened that this bubble they found on the left here is a lot faster and performs better. So those are the new superoptimization, new superoptimizers. A quick word on the instruction set you use. So this was partly come out of some of the stuff I did over the summer, in that it turns out the instruction set you use for your superoptimization has a huge effect on how efficient the search is. So while I said earlier, if you have a larger instruction set, you have to explore more, so you have more sequences to consider. If you have a smaller instruction set, you actually tend to need longer sequences to find the correct solution, which is perhaps obvious, but if you have half the instruction set, you've only got half as many instructions, you're going to need to combine those in more different patterns and have more code. So this is actually a problem for the superoptimizer because the number of sequences scales exponentially with the length. And if the actual exponential equation tends to bias it, if you have a really complex instruction set with lots of instructions, you can actually do a better search, a quicker search, because you don't have to consider as long a sequence. So I ported the GNU Superoptimizer to AVR, and it turns out that AVR is particularly difficult to superoptimize because it's got a very simple instruction set with very simple operations, and you have to chain loads of these operations together to get your target function. So what would take 5 instructions in one instruction set takes a couple more in AVR because it's a simple 8-bit instruction set. So that is new stuff in superoptimization. And now I'm going to talk a bit about the GNU Superoptimizer, GNU's open source superoptimizer. So I'm going to talk a bit about what can it do. I'm going to talk you through how we can add a new goal function, how you can do this yourself, and then adding new architecture. So covering a bit of GNU Superoptimizer's internals as well. So what can it do? This is the sign function again. If you have a negative number, return -1. If you have a positive, return 1. If you have 0, return 0. And on the right there is what the compiler spits out for OS. So we're compiling for code size here, making it as small as possible. And on the right, on the left here, we have what the Superoptimizer produces. And it does a lot better. It's 5 instructions instead of 11 instructions. In certain circumstances, the compiled code is actually faster, taking 4 cycles, but that relies on R0 being initialized to 0 already, which the compiler doesn't by default. So good results with that. It produces sequences of code that you can just slot into your applications. So features, it's got lots of architectures. It's now got AVR, it has an old variant of x86, it's got Spark, it's got MIPS, PowerPC, XMOS. There's no ARM port. Apparently there was a patch for it somewhere, but that patch disappeared. It's quite easy to add new goal functions. There's just a file with a very easy format. You can add a bit of code in and it will superoptimize it for you. And there's some features, so you can turn on different parts of the instruction set. If you don't want to use the carry instructions, then you can turn them off. If you want to use all possible shifts or certain subsets of instructions, there's flags to turn those on and off. So how does this work? So it's I'll go a bit more in depth about the algorithm uses for searching. So it starts off by just exploring everything in one instruction. So sort of add and check that if they're broken. Then it would check the next instruction, check the next instruction, and so on. Then it would see, oh, we've checked all of the single instructions, let's check 2 instructions. It would then recompute, add, then the next instruction, do another add and check. And we go on, it's to 2 levels now. It will check each instruction in turn, onwards. And with 3, you can see is this nice demonstration of how quickly everything explodes, because I can't even put it on a slide. So already there's 3 to the power of 3 different possibilities. So most of the architectures in GNU Superoptimizer get to 4 or 5 instructions before you're there waiting for days for it to happen. So that's iteratively deepening deep depth first search, and what the GNU Superoptimizer uses internally to search through all of the instruction sequences. So, how to add a new goal? So there is a file goal.def, and there's a bunch, there's about 30 of them in there already, and they're all in this format. You define a goal, you define an identifier for it, a name, and then the actual code at the end. So it's quite easy. You just give a unique ID, the number of arguments, and a name, and then you put your code in there. And the code's in a specific format. You need to put, you can only have 1 result, and you've got up to 4 arguments. So that's quite easy. Then it'll just appear in the interface. You can do GNU Superoptimizer -f, then your name, and it will superoptimize it for you. So how to add new architecture? That's also not too hard. There's various things you need to define. You need to define stuff like the bit width that you're targeting. You need to define new instructions if there's any unusual things that it does which other processes don't do, and they're all defined as macros in the header file. And then you need to add your own section into the synth file, and all this does is, as the iterative deepening depth first search is called, you will branch to your instruction. You will go through all of your instructions that you need to execute. You'll first perform the instruction, then you'll check all of the descendants from it. And if you add a declaration for each of your possible target instructions or your architecture instructions, it will automatically do it. So that's a very high-level view of how to add an architecture. Future improvements. So I'm planning on adding some additional features to GNU Superoptimizer at some point. But my main one I'd like to add is some form of parallelism. So currently it's single-threaded and extremely intensively single-threaded. But it's also very easy to split out into multiple cores and then eventually to multiple machines. There's no reason why it should be able to do that. It's fairly comparatively parallel. There's other things that would be nice to add. You could do some sort of range analysis. You could say, well, I only want my instruction sequence to work for these particular values of input, and then that might open up a whole set of different results which can compute the result you want for those specific values, but go way off if you don't have those values. And then implement some of the other wacky features such as machine learning to guided search and different representations, plus verification. So, conclusion, superoptimization is expensive. It's still pretty expensive, but less expensive. It's getting better. We've got some new techniques, and those techniques result in some impressive speed-ups in code. And the GNU Superoptimizer I've uploaded there, and with some of the new ports and new improvements that I've added. Thanks.
Thank you, James. Got time just for a couple of questions. Any questions on this?
Yeah. It sounds like you should merge this with the previous talk.
That's why we've been talking to Phil Ridley and how the talks came together, because we are putting in a proposal under the new Energy Efficient Computing Initiative for him to have 4 months next summer using 80,000 cores. And we bid for 2 million cores or something. 2 million core hours.
Especially if I've understood that peephole one, that really you need a library, the building up a library of tools. And so we
Depends on the construction, but typically there was a LVM pass in the back end for that particular Superoptimizer, which back to it. So there's a couple of passes. So the harvester was a pass in the LVM backend, which just extracted sequences at the very end of the compilation, as well as, and then the enumerator was just a completely offline thing, not connected to the compiler. So it would go through all of the instruction sequences and then look up in this hash table.
Yeah, maybe my compiler knowledge is too old. It kind of sounds like if you generate a certain, you have your whatever your tokenized input, and then you kind of match that to intermediate code stuff. But then if you then that gets translated into your low level. But it's possibly at that point that it would be really nice to have a whole library of just better ways to do that.
So the actual peephole pass would sit somewhere in the middle like that. It usually sits closer towards the end of the compiler in the back end, rather than the tokenizer stage. I mean, there's another nice use for it in that you can, if you associate the harvester to pull in at a very high level IR, you can enumerate at the very low level, and then you don't have to do any sort of code generation. You can just match the constructs you get at the very high level and use that database to lower it to the constructions. So you can do binary translation of it. That's another use for it.
So then it would be good to have your great big platforms computer to work out all this stuff and just enumerate it, and you just do it once and that's it.
Yeah.
Great.
Yeah, that's
Okay. Yeah. Carry on, please.